two thin films, a layer of copper or aluminum between them as an electrode. The whole stack is thinner than a credit card. When a raindrop hits the top surface, the impact transfers electrons between the materials. Those electrons flow through the electrode. That electron flow is current. That current, routed through a circuit, is electricity. The material cost for 1 square meter of this stack is less than $20. It has no moving parts. It produces no emissions. It does not require sunlight. It generates electricity every time it rains, which is precisely the moment your solar panel output drops to near zero. This device exists. It has been verified by Georgia Tech, the Chinese Academy of Sciences, and published in Advanced Materials. It is not in production. It is not on your roof. And the answer to why not is more complicated and more honest than any suppression narrative would make it. The triboelectric effect is not new physics. You have experienced it every time you shuffled across a carpet in dry air and reached for a doorknob. A charge built up on your skin from friction between your feet and the floor. The snap when you touched the metal was that charge discharging. Ancient Greek philosophers documented the triboelectric effect in amber. The word electricity derives from the Greek electron, meaning amber, because rubbing amber with wool produced a visible static charge. That observation is over 2,000 years old. The physics was known. What no one had built was a device that could harvest that charge efficiently enough to be useful. In 2012, Zhonglin Wang, a materials science professor at Georgia Tech, born in Zhejiang, Hunan Province, China in 1955, published the first triboelectric nanogenerator in the journal Nanoenergy. His motivation was not commercial, it was thermodynamic. The vast majority of mechanical energy in the environment, raindrops, wind, footsteps, vibration, is too low frequency and too irregular for conventional electromagnetic generators to harvest efficiently. Wang identified that triboelectrification and electrostatic induction together could convert that low-frequency, irregular motion into electrical current with no rotating magnets and no minimum speed threshold. But here is what most coverage of this technology misses entirely. The physics of a TENG operates on 3 compounding principles simultaneously. Triboelectrification creates surface charge when 2 different materials contact and separate, the same mechanism as your carpet and the doorknob. Electrostatic induction creates a voltage difference between the electrode and ground when that surface charge moves. And a rectifier, a one-way valve for current, converts the alternating charge flow from repeated raindrop impacts into direct current your devices can use. The result is a device that produces electricity from mechanical energy that was previously uncapturable. Not because the energy wasn't there, because no one had built the right harvester. Wang's original 2012 device produced milliwatts. By 2013, Georgia Tech had published a nanoparticle-enhanced TENG small enough to fit in a human palm. That generated 1.2 watts of instantaneous output from a single footstep, enough to light 600 commercial LEDs in real time. That same year, the Georgia Tech Office of Technology Licensing filed for commercialization rights under the description of harvesting large-scale mechanical energy from rolling wheels, wind power, and ocean waves. By 2018, Wang's team reported that a square meter of single-layer TENG material could produce as much as 300 watts. That figure requires immediate context. It is an instantaneous peak output under optimal mechanical excitation conditions, not a continuous average. The distinction matters enormously, and the research literature is clear about it. But the trajectory of improvement was documented, a factor of 100,000 increase in power output density between 2011 and 2018. The raindrop application specifically emerged as a research focus around 2015. When a transparent TENG published in Nature Scientific Reports demonstrated electricity generation from flowing water at 11.56 milliwatts per square meter. By 2021, a gridded TENG array published in ACS Applied Materials and Interfaces achieved 8.56 milliwatts per square meter specifically from simulated rainfall, 245 times the output of an ungridded device under the same conditions. But the real question is not whether it works in a lab. The question is whether it works on your roof. And that answer is more complicated than the data suggests. The most significant paper in the Raindrop TENG literature was published in Advanced Materials in January 2023 by a team led by Zhonglin Wang at the Beijing Institute of Nanoenergy and Nanosystems. The paper integrated a triboelectric nanogenerator array directly with a silicon solar panel, the same panel technology on residential rooftops across the United States, and measured the output of both systems side by side during actual rainfall. The result was specific and striking. In rainy conditions, the Raindrop TENG array produced an average power density of 40.8 milliwatts per square meter. The solar cell produced 37.03 milliwatts per square meter under the same rainy sky. The TENG outperformed the solar panel in the weather condition where the solar panel is weakest. That number deserves translation into practical terms. A residential solar panel produces between 150 and 220 watts per square meter in direct peak sunlight. 40 milliwatts per square meter is roughly 1/300th of that output. But during rainfall, when your solar panel produces near zero, 40 milliwatts per square meter across a 30 square meter roof is 1.2 watts of continuous output. Not enough to run your refrigerator, enough to power a remote sensor array, a weather monitoring system, or a string of LEDs indefinitely without any battery or grid connection. But the real engineering finding here is not the absolute output. It is the complementarity. Solar generates maximum power in the weather condition where TENG generates nothing. A roof that carries both systems is a roof with no weather-dependent dead zone. The Nature Communications paper published in August 2024 extended this principle further, integrating a TENG with a radiative cooler to create an all-weather device that harvests rain energy on wet days and saves cooling energy on sunny days from the same surface. The research institution was the Beijing Institute of Nanoenergy and Nanosystems, working in collaboration with international partners. The device was fabricated on glass, transparent enough to integrate with windows, not just roofs. 3 named research institutions across 3 continents, Georgia Tech in Atlanta, the Chinese Academy of Sciences in Beijing, and international collaborators have all confirmed the same underlying physics independently. The energy is real, the device works. And this is where the honest answer starts to depend on who is asking. But these numbers come with an important caveat, and it is a significant part of the reason why this technology is not on your roof right now. The first limitation is the output gap. The most advanced Raindrop TENG published in peer-reviewed literature produces roughly 40 milliwatts per square meter under rainfall. A residential solar panel produces 150 to 220 watts per square meter in direct sunlight. That is a gap of roughly 5,000 to 1. The average American home consumes approximately 875 kilowatt hours of electricity per month. A TENG array covering an entire residential roof of 100 square meters operating during every rainy hour in a high rainfall city like Seattle, which receives around 150 rainy days per year, would produce approximately 1,440 watt hours annually. Your home consumes 10,500 kilowatt hours per year. The TENG covers less than half of 1% of that demand. Science Advances published a comprehensive review in 2024, documenting the core engineering challenge directly. Traditional TENGs produce high voltage and low current, a combination that makes them efficient at sensing but difficult to use as stable power supplies. The internal impedance of a TENG is typically in the mega OHM range. Your household appliances are designed for systems with internal impedances in the milli OHM range. Connecting a TENG to a standard electrical load without power management electronics wastes most of the generated energy before it reaches the device. The second limitation is durability. A 2023 review in Advanced Functional Materials documented the core problem. The triboelectric surfaces wear against each other over thousands of cycles. For rain impact TENGs, where the mechanism is droplet contact rather than friction, wear is less severe. But UV degradation, humidity cycling, and temperature extremes on a residential roof represent conditions that have not yet been validated over a 10 to 20 year product lifespan. The third limitation is the absence of a manufacturing pathway. Roll-to-roll fabrication of TENG films has been demonstrated in laboratory conditions. No commercial production line exists. No UL listing exists. No building code in the United States has a provision for triboelectric energy devices. The technology cannot be installed, inspected, or insured. The market explanation is structural, not conspiratorial. A standard residential solar panel delivers kilowatts. A TENG delivers milliwatts. No installer, insurer, or utility has a business case for a device. That generates 0.5% of a home's electricity demand, at a manufacturing cost per watt that has not yet been established because the manufacturing process does not exist at commercial scale. It is not banned. It is not suppressed. It is simply not yet competitive with the technology it would need to complement, and the gap is measured in engineering years, not corporate decisions. So the honest question is not why this technology is being hidden. It is whether it belongs on your roof right now, and if not now, when. If you are a homeowner looking for a primary electricity source, the answer is clear: solar wins. Solar delivers kilowatts per square meter. TENG delivers milliwatts. A solar panel with battery storage covers your home's electricity needs across all weather. A TENG does not. If you are a sensor network operator, a remote monitoring system designer, or someone who needs continuous low-power output specifically during rainfall, the 2023 Advanced Materials paper demonstrated a self-powered wireless light intensity monitoring system running continuously on Raindrop TENG output alone. No battery, no grid connection, no solar, running in the rain. The competitor product that wins for primary home electricity generation is a solar panel with lithium iron phosphate battery storage. Not because it is better in all conditions, but because it covers all conditions at a scale that matters. A TENG covers a specific condition extremely well. The engineering question is whether that specific condition is worth adding a second surface layer to your roof. The honest answer right now is probably not, unless you are building infrastructure that specifically needs power during rain. Zhonglin Wang began working on triboelectric nanogenerators in 2012 because he saw a thermodynamic problem no one was solving. The mechanical energy in raindrops, in wind, in footsteps, in ocean waves, energy that arrives continuously and dissipates uselessly, had no efficient harvester. He built one. Since then, his team has increased its power output density by a factor of 100,000 in 12 years. That trajectory matters. Solar photovoltaics followed a similar trajectory, from milliwatts to kilowatts over decades of engineering investment, driven by manufacturing scale and material science breakthroughs that were not predictable from the first laboratory demonstration. The TENG is not there yet. The honest reading of the 2023 Advanced Materials paper is not that TENG is ready to replace solar. It is that TENG produces more power than solar in the specific weather window where solar produces nothing, and that finding was published in peer-reviewed literature by a team at one of the world's leading materials science institutions. The rain on your roof carries energy right now. Every drop. The physics to capture it has been proven. The manufacturing scale, the durability standards, and the power management electronics to make it useful at household scale have not. That is not a conspiracy. That is an engineering timeline, and it is shorter than most people realize. If you want to understand how the same triboelectric physics applies at the scale of ocean waves, where the energy density is thousands of times higher and the engineering pathway is much closer to commercial deployment, that analysis is in the next video.